Science is everywhere around us, even in art. Glass fusion involves the material science down to the molecular level. Fusion is the process of joining two or more things together to form a single entity. Glass-fused jewelry is a unique art, an art that incorporates science in every step of the process. Coefficients of expansion, COE, play a big role in fusing glass. While fusing, glass gets heated to over 1,000 degrees Celsius. Differences in the glass types will make it hard to fuse together. The fused glass will crack due to the different coefficients of expansions. Even a difference of just 6 in the COEs will make the glass crack. For example, COE 90 versus COE 96. Then, the idea of fusing glass and metal sounds even more exotic. When fusing glass to make necklaces, there needs to be a hook attached to a necklace cord to the glass pendant. This does not look very artistic. One also needs to know which metals will break the glass and which metals won't. My hypothesis is that finding glass and metals that expand at the same rate will fuse together without cracks. As materials warm up, they get longer. The heat is transferred to the molecules of the material, which then vibrate, resulting in an expansion of the heated material. Every material has its own coefficient of thermic expansion. In the equation, alpha is the experimental expansion coefficient that is unique to each material. In order to find alpha, one has to measure the length expansion of a material over a given temperature range. COE stands for the coefficient of expansion. The glass I am working with is classified as COE 90. COE 90 means that for each 1 degree Celsius in the temperature increase, the glass expands 9 millionths of an inch. Another common fused glass is COE 96. The difference between these two expansion coefficients is 0.000006. This is very minimal, yet very dramatic on the molecular level. This is the oven I used to heat up the glass with the metal rods. There is a temperature control. I programmed the oven to heat up to 1,625 degrees Celsius. It is important to heat up and cool down slowly due to the expansion of the materials. Inside the oven, you can see the hot glass. This table shows that titanium has a very close COE to the glass I used, but rather a high melting point of 1,668 degrees Celsius, compared to the glass of 787 degrees Celsius. The aluminum has a melting point below the glass, and the copper has one slightly above. Their COEs, though, are quite high with 248 and 176. You can see the different types of metals here. Even though titanium sounded really appealing with its COE value, I realized that I also needed to look at how soft the material is because I needed to make a hook with the metal to hang as a necklace. Aluminum and copper are bendable enough to make a hook with the necklace. Now let's look at how the metals fused with the COE 90 glass. Here are the results of fusing metal and glass. Each metal was heated 4 times with COE 90 glass. I could not find any deviation within the 4 tests for each metal. Here you can see the aluminum with its corresponding wire sample. The aluminum did fuse with the glass on the outsides. The next is the copper wire. You can see the same thing for the wire as the aluminum. It did fuse on the outsides. The next is the nickel. As you can see here, the nickel rod detached from the glass. The next one is multi-purpose stainless steel. This one broke the glass when it was heated up. The same result happened for the high-temperature stainless steel. It also broke the glass. The last one is titanium. This one worked nicely with the glass, but because of its hardness, I could not use it as a wire.